In the homology of configuration spaces.
Great, yes, thank you. It's a pleasure to be here, so thank you all for coming. That's great. So in very broad terms, in my recent research, I've been interested in using tools from category theory, from representation theory, from commutative algebra to study objects that come from geometric group theory and from topology. And I thought for this talk, to keep things a little more concrete, I would just choose one application of this broader program and focus on that. So as advertised, today I'll be looking at configuration spaces of points in a manifold and say something about structure and patterns that we see in the homology of these configuration spaces. So, great, so here's...
Jenny, it would be better not to go so far left.
I should go, oh, where?
Yeah, that's
This is good? Okay, great. I will restrict myself. We passed this line. Okay, so the main definition of the talk is the following. If M is some topological space, then I can define the ordered configuration space on M on K points as follows. So this is the space of ordered k-tuples of distinct points in my space M. So this is a subspace of the k-fold Cartesian product on M and is topologized as such. You can view these spaces as this sort of complement of a subspace arrangement. So you can view it as taking the k-fold Cartesian product and then deleting all the subspaces you get associated to those points where two or more of the coordinates coincide. So one of the most basic examples, if you take M to be a circle, then the ordered configuration space of the circle on 2 points, I can construct by taking a circle across a circle, that's a torus, and then just deleting the diagonal. And so exercise, the resulting space is topologically an annulus. So here's one of the most basic examples. Another way I can think about these spaces is as some sort of embedding space. So this is the space of embeddings of the the discrete set on k points into M. And so from this perspective, I can think of points in my configuration space as being pictures like this one, where I have k distinct points that are labeled with 1 through k. Okay. So these configuration spaces, these ordered configuration spaces, come with an action of the symmetric groups. The symmetric group acts by permuting the k-tuples, equivalently by permuting the labels on my distinguished points. And this is a free action. We've deleted precisely those points in the Cartesian product that would have had non-trivial stabilizers under this action. And so we get a nice covering construction. And the quotient space is called the unordered configuration space. So I can view view this quotient map as being precisely the map that takes a point in my ordered configuration space and then simply forgets the labels on the points. And I can view the unordered configuration space as the space of k-element subsets of M. Okay, so here's another exercise in visualization. I claim that if you apply this quotient map to the configuration space of the torus, then the result is topologically a Mobius band. If you take the quotient of this picture by the involution that reflects. Okay. Great. So the object of our project was the following. We were interested specifically in the case where M is a manifold, and even more specifically, M is a connected non-compact manifold. Maybe a smooth manifold of dimension at least equal to 2 and of finite type. So by finite type, I mean I'm going to assume it's homotopy equivalent to a finite CW complex, which is an assumption that ensures that the homology of my configuration spaces are all going to be finitely generated as groups. Okay. And then our goal, the goal of this project was to say something about the homology of these configuration spaces. All right. So let me maybe comment a little bit on how we might think about these homology classes in this case. So right. So I mean, one key fact, of course, is that homology is functorial. So our homology groups will have an induced action of the symmetric groups. And so this is not the definition of homology, nor is it precisely true, but it's very close to true. It is almost the case that we can think of elements in these homology groups as being represented by maps into our configuration space from closed manifolds. Okay, so it is almost the case that these are groups whose elements are maps. I'm sorry. Closed manifolds. Okay. Up to some equivalence. And toward the goal of understanding these particular homology groups, I guess there's some good news and there's some bad news. So some good news about these homology groups is that it's really easy to come up with lots and lots of examples of homology groups in these configurations, of homology elements in these configuration spaces. And in fact, I can draw you a picture of some of these. Oh, and the chalk, beautiful, fancy colored chalk. All right, so let's get some colors. And with these colors, I can draw you a picture.
Psychology test.
Oh yeah, which ones? All right. Well, hopefully these ones are visually distinctive. Oh, except for maybe if you're not red-green color blindness, probably choose different colors. All right. So, so I can just draw you pictures of elements in the homology of these spaces. So let me draw some pictures. Okay. So this picture is a picture of a 2-parameter family of points in my configuration space. Because these two loops are disjoint, I can run them both independently while staying inside the configuration space. And so what that means is that this is a picture of S1 cross S1. This is a picture of a torus in my configuration space. And as such, at least up to sign, this specifies an element in degree 2 homology. So up to sign, this is a torus in the configuration space of M on 3 points. And up to sign, this gives me an element in its degree 2 homology. Okay. And so I can think, in a sense, this first loop I've drawn somehow comes from the homology of the underlying manifold. And the second loop that I've drawn comes from the homology of configurations of Euclidean space. And so from those two starting points, it's possible to write down, to draw pictures of lots and lots of examples of elements in homology. So it's easy to come up with homology classes. Unfortunately, however, the understanding the relations between these classes is a very subtle problem. So even the question, here's a class I drew for you, here's an element in H2, is this element 0? In general, these questions are subtle. So a hard question is to understand the additive relations or between classes produced in this way. I can tell you, this particular picture I've drawn, this element is non-zero in homology. But something a little bit subtle is it happens to be the fact that if I were to delete the point number 1 and just consider this loop that's left as an element of H1, that element in H1 is 0, which is maybe surprising because the same homology class in configurations of the plane is non-zero. So somehow having this piece of genus here killed this class. And that I think is subtle. So that was surprising to me when I first learned this fact. Okay, so in general, actually computing these homology groups is difficult. We understand them very, very well in the case that M is Euclidean space or punctured Euclidean space. And I think in virtually no other cases do we know what all the homology groups are of all the configuration spaces. In fact, to the best of my knowledge, for the ordered configuration spaces, we don't even know all the Betty numbers of the configurations for a torus. So doing computations, or at least doing certain types of computations with these groups, is a challenge. Okay, so great. So that was the bad news, that computing is hard. But yes, let me demarcate the acceptable bounds on the board. Come back here. Okay, so I should say for the unordered configuration spaces, there was work done last year using factorization homology to compute the Betty numbers for unordered configurations in the torus. So that was something due to Ben Knudsen, I believe, that was new as of last year. Okay. Right, but okay, so there's more good news about the situation. And the more good news is that we have more structure.
So that's not really a torus, is that what you meant?
Oh, I'm sorry.
That's not a torus.
This is a punctured torus. We also do not know. So for these configuration spaces, the homology is computed in low degree or for a small number of points. But in general, we don't know what the groups are. or what the betting numbers are.
You emphasize that you're looking at non-compact manifolds. Are compact manifolds essentially different?
So I can comment on the distinction there. Shortly, I'm going to define some maps on configuration spaces that require the non-compactness to be well-defined. So I specified non-compact because I guess these ones give us access. They have extra structure that allows for the analysis that I'll show. There are other things you can say about compact manifolds, but that's maybe a topic for a different talk. So I'll point out where I'm using that assumption later on. Okay, right. So the good news is that these homology groups come with more structure. And the approach that algebraic topologists have taken to this problem for many, many years is the following. That what we should do is fix the manifold M, and then then package together all of the homology groups of all of the configuration spaces of M into a single algebraic object, and specifically as, an object having the action of some category that has this extra action, this extra structure that comes both from the symmetric group actions and from certain topological operations that I'll define in a moment. And so, having done this, we're now in a framework where we can draw on tools from commutative algebra and homological algebra, algebraic topology, to say structural things about this sequence. So that's the framework for this program. And to that end, I will describe, for the rest of the talk, 3 different generations of stability results on the homology of these configuration spaces. So, the first extra input that I need is the following. Because we assumed that the manifold in question is non-compact, it's a fact that we can construct an embedding of the disjoint union of M and Euclidean space into M in such a way that the embedding of M is isotopic to the identity on M. And so here's the picture. The point is that because M is open, it is possible for me to find some self-embedding of M into itself in such a way that I can find a copy of Euclidean space in the complement of the image. So here's our picture of the embedding. And with this embedding, we can define maps between our configuration spaces and talk about stability with respect to those maps. So the first result that I'm going to share comes from pioneering work of Dusa McDuff from the 1970s. So the first result is about the unordered configuration spaces. Okay? And to state this result, we need the following operation. So define, we'll call this the stabilization map, as homologists do. This is a map from the configuration space on k points into the configuration space on k+1 points. That's defined as follows. So given a configuration, an unordered configuration on k points, what we can do is map that configuration, map that point in configuration space into configuration space on one more particle by taking this configuration and mapping it to its image under the embedding. So I'll map this guy to here, and then introducing a new particle out in my copy of Euclidean space. Okay, so here we can, what we're doing is we can map this particular configuration, this point in configuration space, to its image under the embedding in the image of M. And then we can introduce a new point in our copy of Euclidean space.
Don't you lose the unordering then?
Don't we lose the unordering?
I mean, isn't there like this new point is kind of special?
This new point is kind of special. So this is still a point in the unordered configuration space. And so it's true that the image of this map lies in a very particular subset of this configuration space. But this is still, these points are still unordered in this case.
By definition.
By definition. Yes, I haven't labeled them. Right, and it turns out that to define this map, we are really genuinely using the assumption that the manifold is non-compact. In general, such maps do not exist for arbitrary manifolds. You need some extra structure on the manifold, such as non-compactness, in order
Why
to
not
get
to
that
add just a
result.
special point over there?
I beg your pardon?
Why not to add just a special point? Do you care about dimension or about what?
So, sorry, the question is why not label the point? Or
No,
why?
just take a specific point. Why to put the Euclidean space for choosing this point?
Oh, yeah, so in general, why can't I just add a point? Yeah, right, so I guess the problem is if I just choose a point in my manifold and say add a new point there, for points in the configuration space where there's already a particle at that point, the result won't be in configuration space, so I'd have to find a way to sort of nudge those two particles apart, but I can't always do that
He was
continuously.
wondering why you bothered to put an RN, just choose
Oh,
a
why not
point.
choose a point? Oh, I see what you mean. I see what you mean. Why didn't I just choose the disjoint union of n and a point?
Yeah.
Ah, yes, that's a great question. That will become evident at the very end of the talk, when we stabilize by an operation that's more complicated than just adding a point. Yeah, that's right. So for the first two generations of stability results, it will be enough to just choose a point in the complement. But later on, I'll want the full Euclidean space structure. Great. Okay. Great, so here's the stabilization map. And then this result that was originally due to McDuff, and later Siegel gave a new proof that gave a quantitative stable range, both in the 1970s. And the result is the following, that if we fix the manifold M, and we fix the homological dimension I, and consider the induced map by T on the I homology of our configuration spaces, then once K is large enough, so specifically once K is at least 2 times I, these induced maps will be isomorphisms.
So here you've now brought in the ordering to this?
Oh, no, I'm sorry, I wrote the wrong thing. Thank you, thank you. No, sorry, I apologize. This is a result of the unordered configuration spaces. I'm glad you caught that. Great, okay, so again, what this says, if I fix I fix the homological degree, and I start to add more and more points in, slide in more and more points at the boundary, and look at the induced map on homology, once K is large enough, the homology groups stabilize. So this says something like the I-dimensional structure of these configuration spaces, at least as measured by the homology groups, stabilizes as the number of points increase. Okay.
So does that prove all the beta numbers are finite?
Yes.
Only the stable ones.
So right, that's right. This proves that that stably they're finite. And that's right. I'm using, in fact, this assumption might not be necessary for this proof, but I assumed earlier on that M was finite type, which means that these are all
Oh, so they're all
finite groups.
First
Or
few are
finite rank groups. Oh, sorry, I said I assumed some of the assumptions on M imply that these homology groups are all finite rank.
For fixed K.
For fixed K, that's right.
Yeah.
Very good. Okay, so, great. So this is a result from the 1970s. And more recently, there has been renewed interest in the ordered configuration spaces. So the next generation of results, maybe I'll call representation stability. And these concern the ordered configuration spaces. So, right, so a question that we could ask, maybe a naive question, but a question that we could ask is, again, these ordered spaces give me a nice sequence of spaces. And again, we have this analogous stabilization map. So again, in this case, there's the stabilization map that takes an ordered configuration and introduces a new particle out near the cusp. This time we'll introduce the particle labeled k+1. So again, this gives me a nice embedding of my configuration space on k points into my configuration space on k+1 points. So we could ask the question, maybe these spaces are also homologically stable. But the answer to this question is they are definitely not. We can see this in the easiest, the sort of most basic example of such a group. So the question is, could these ordered configuration spaces be homologically stable? And the answer is no. And we can see this even if we look just at the degree 1 homology groups of configuration spaces of the plane. So the configuration spaces of the plane, this happens to be a k-pi1 for the pure break group. These are groups that maybe Arnold first computed them in the late 1960s. And in degree 1, these groups are as follows. So it's a free group of rank k choose 2, which tells me this group is growing quadratically in rank. This group has no choice of being stable in the sense of the theorem of McDuff. But I can tell you exactly what these elements are. So if this is my plane, and here then for every choice of two particles, I and j, is particle I and particle j, I can write down an element in homology by letting the particle labeled I run in a circle, say, counterclockwise around the particle labeled j. And it turns out that these elements are additively independent and generate all of my degree 1 homology. So these, for each choice of I and j, these are all the generators of my homology. And so even though this group is growing quadratically in rank, this picture shows us that in a sense, up to the action of the symmetric group, up to relabeling of these particles, these elements all look sort of the same, and they all look like they're coming from just the configurations on 2 points. And so this is basically the philosophy behind this representation stability program, that even though these groups are all growing polynomially in rank, up to the action of the symmetric groups, somehow they stabilize. Okay. Very good. So here's the next theorem. This next theorem was proved by Church and Church-Ellenberg-Farb in the 2010s. Okay, so if we again fix homological degree I and fix M, in their version they assumed M was orientable since they were working with a spectral sequence due to Jotaro that required this orientability assumption. What they proved is the following. So we have this new stabilization map. Let me name it T prime. That gives embeddings of our ordered configuration spaces. Okay, and again, we can look at the image of the induced map by T prime on my ith homology in configurations on one more point. And it's no longer the case as before that this is going to be an isomorphism in general. But what is true is that now, if you take the orbit of the image of this map under the symmetric group, then that will span everything. So up to the image of up to the action of the symmetric group, this image generates everything.
So that last cyclic piece you have to add.
Once k is large enough.
There's one more cyclic piece you're adding, because the symmetric group's getting bigger. And the first one, most of it's varying already.
Yes, that's right, that's right. So this is, I mean, by definition, this piece is a representation of SK.
Yeah.
So now I'm hitting it with this larger group, SK plus 1. That's right, and so that will actually move this group around in here, and the result will span this entire homology group as soon as k is large enough, as soon as k is at least 2 times I.
How close are these two theorems, actually? If you're acting with the symmetric group, then is it similar to forgetting about the order?
Oh, right. So here's one relationship between these two theorems. So as stated, these are both theorems about integer homology. This argument doesn't work with integer homology, but if for a moment you let me work with rational homology, because we have this nice covering construction of the unordered space by the ordered configuration space, by some sort of standard transfer argument, I can identify the rational homology of this space, the base space, with the coinvariance under the symmetric group in the rational homology of this space. And it turns out this theorem is actually a lot stronger than what I've written down here. But one consequence of the stronger version of the theorem is that the multiplicity of the trivial representation has to stabilize in these homology groups. And so rationally, this theorem implies the rational version of the theorem there. But I do not believe that, as written, I don't think the integral version of this theorem implies the theorem that I've written.
I thought about vice versa. Here it is about not only about generators, but also about relations. Here, what about relations?
What about relations? Ah, yes. So I am not going to state the full version of the theorem, but in fact, we can say something about relations in this case. So let me make a couple of comments. So and then I'll get back to that comment and say something about relations, because we actually
There is some version here about relations.
there is a version here about relations. Yes, yes. So that's right. So another way to say this is if I take this group for k points and I induce it up from sk to sk plus 1, then what this says is that I get a surjection onto this group here. And in the stable range, we understand the kernel of those surjections. So there is a stronger version of the theorem that addresses relations. But I'll comment more on that in just a second. Great, so the first comment is a remark that a nice feature of the methods that we used, Jeremy and I used in this project, allowed us to give a new proof of this result that did not require the orientability assumption. So one remark is that our paper gave a new proof that works for non-orientable M. And also works for M that are not of finite type. And so that's one remark. And I wanted to draw us a picture of how we might think about this result. So the theorem, in a sense, says the following. The theorem says that if I look at the degree I homology of my configuration spaces, then these groups are spanned by, at least speaking informally, this is not a precise statement, but it's a good picture to have in mind. Speaking informally, these homology groups are spanned by classes that come from pictures where I have at most 2i points that are actually running around the topology or running around each other. And all of the remaining points are just sitting static out at the cusp, out in their copy of Euclidean space. So it's spanned by classes that have at most 2i points that are, informally speaking, running around the topology or swimming around each other. And the remaining k minus 2i points are just static out in our copy of Euclidean space from our embedding. And so this picture, I think, again, sort of helps explain the growth of these homology groups. It turns out that they're growing like a polynomial. They're growing in rank polynomially of degree 2i. But that is precisely because k choose 2i is the number of ways I can choose these points to sit out at the cusp. And that's polynomial of degree 2i.
Why 2i? Why even?
Why 2i? So,
Why just a single point cannot run around the hole?
oh yeah, certainly I can have more points sitting still out here, but I need at least k minus 2i points that are not moving around. And then, that's right, and then the question of why 2i is a stable range, I think, is a slightly deeper question. But it's something that you can see very concretely even with the pure braid group.
So it's at least,
It says at most 2i.
At most 2i points out here, and sorry, at least
and therefore,
Maybe one.
at least k minus 2i points are sitting still over here. And again, this picture kind of illustrates the fact that all of these homology classes are really coming from configurations on 2i or fewer particles.
the 2i is a sharp bound on stability.
2i, that's right, 2i is the bound. It is, I think you can find examples of manifolds where you can get better bounds, but
Yeah.
it is sharp. It's the strongest thing you can say about all the whole class of manifolds that I put up before. All right, oh yeah, so let me go back to this question about understanding relations for these things. So maybe I won't get into detail on this point, but what's going on in the background of this result is that the framework is that we have somehow packaged together this whole sequence of homology groups and are viewing it as a module over a category that is encoding both the symmetric group actions and these topological operations that introduce a point. And so the result, in those terms, the result that I stated here is the statement that this module, this sequence, is finitely generated with generators in degree 2i and below as a module over this category. But in fact, something stronger is true. There's a strong sense in which this module is free as a module over this category. And I guess it's free in some technical sense that, like, you know, the sequence, this module is in the image of the adjunction to some free functor, or some forgetful functor rather, or something of that sort. But in concrete terms, it means that if you know what the groups are in degrees for 1 through 2i points, then there's a very deterministic way that you can build up every subsequent group in the sequence. So this other remark is that the theorem is stronger than what I've stated there. The sequence of homology groups is free as a module over a certain category that's encoding all of these operations. Category. And it is free. It is free on a collection on certain subgroups of the first 2i groups. So hi f1m up to hi of f2i of m. So there's some collection of subgroups in these first 2i groups that we call the unstable homology. It's unstable in the sense that these are the groups that are not in the image of this map. And every subsequent group, every subsequent homology group in the sequence is built up from these unstable groups in some well-understood way. there's some nice formula that involves inducing up that is easy to write down. So, I mean, again, I should stress that it's quite hard to do computations with these homology groups. So there aren't that many cases where we can compute very much. But at least in principle, this means that if I could compute the first 2I terms in this sequence, then I could write down all of them. Okay.
Is it like a spectral sequence, or is it some real deterministic procedure?
No, it's very deterministic. It's like I'll write it down for you. If I have, so suppose I have an unstable group I'll call V in degree m for k equals m. Then the contribution of this unstable homology group to every future group in the sequence is going to be, so its image in every future group for all larger k is going to be the induced representation Sm times Sk minus m induced up to Sk of V tensor the trivial representation. So in other words, this is the same as saying the following. I'm going to take the sum over all m element subsets of the set on k elements. And for each such subset, I'm going to take a copy of my unstable group V. And now this is a representation of Sk, which acts both on V and by permuting the sum ends. And this is the form in which the unstable groups, so I do this, I take the sum over the unstable subgroup in each piece from 1 to 2I, and then that will tell me every
The problem
future
is
group.
computing the unstable.
Exactly, that's right. So once you know the unstable groups, this is very easy, but we don't know the unstable groups in very many cases. So.
Is this for the F or the C?
This is for the F. This is for the F. That's right. All right, so let me now state the third generation of results. So this is the objective of my project with Jeremy Miller was to look at patterns that arise between these unstable groups.
Look at what pattern, though.
So what patterns? Yeah, that's the question. So we wanted to show that there are higher order stability results that actually relate the unstable groups in different homological degree. And I'll say right now, so our result holds for general open connected manifolds, but the most interesting case of our result is when the manifold is a surface. And with that said, let me state something about the result. So this project was inspired by a project of Galatius and Galatius Kupers and Kupers Randal-Williams. They have been doing the following. They've been studying situations where you have classical homological stability, like in linear groups and mapping class groups, and groups of this sort. And they've found techniques for showing relationships between the unstable homology in these cases. And they've done so using technology called EN cells, okay, and so that program of theirs, this result, their work hasn't appeared yet, but this program of theirs, I guess, inspired Jeremy and I to investigate these configuration spaces, this SK kind of equivariant setting, to see if in this situation too we could find patterns between the unstable groups. And our techniques are completely different from theirs. We proceed by studying a family of semi-superficial spaces and the associated spectral sequences that come from these configuration spaces. So our techniques are different, but the idea to pursue the project was definitely inspired by this work of Galatius and Kupers and Randal-Williams. Okay, and so here's our third stabilization map. This map is a little bit different from the other two in a few ways. One is that this map is defined right on homology. It's not defined on the space level. This is a map defined right on the level of homology. And this map also has the new feature that it's going to increase the number of points, not by 1, but by 2. And it's also going to increase homological degree by 1. And so here's what this map is. For this map, we're going to take an element in our homology, and we're going to introduce not 1, but 2 particles out in the copy of Euclidean space. And we're going to introduce these 2 particles in a 1-parameter orbiting family. Like this. So we've introduced a pair of particles that are orbiting each other. Labeled k plus 1 and k plus 2 out in our copy of Euclidean space. And so in other words, if I think of this homology class as a map-in from a manifold, what I've done is I've taken a product with a circle and obtained a class in higher degree. And so the main theorem is going to be the weak X stability with respect to this operation. So the theorem, right now we can only prove it for rational homology. And the theorem is the following, that the sequence of unstable homology groups in this diagonal sequence of homology is finitely generated under the action of this map T prime and this symmetric group. So
What does that mean?
See, T prime changes K, but this K is the same over here?
no, so here, sorry, this is K is increasing. So I have this sequence of homology where at each point I'm increasing the number of particles by 2 and the homological degree by 1. And I'm studying those unstable groups in the sense of the last theorem inside each of these groups. I'm looking at that sequence of unstable groups. And the theorem says that those groups are finitely generated up to the action of T prime and the symmetric group actions. So here's the picture that we should have in mind in this case. So again,
How's it quantified? I mean, it's unstable, so wait,
so
there's
just,
no I anymore.
there's no,
Is
oh,
there I
so
that's
here,
I?
yeah, so here's, that's right. So I'm looking at, let me draw another picture in just a
Yeah,
second. I'll draw this picture first, and then I'll draw a second picture. Okay, informally, so there's some stable range. We also don't know the stable range at this point, but there's some stable range R of I, such that the unstable groups in this sequence are spanned by pictures of the following sort. They're spanned by pictures. So first I should say
Between R of I and 2I? Where?
R of I is, we don't know what it is.
No, but I mean, is it above it, below it, or what?
Oh,
It's Everything's moving, I'm getting dizzy.
Everything's moving. I think it should be below it because I want to be in the range where I actually have unstable homology. But then I've re-indexed things there. So let me draw a picture in just a second, and we can sort out what has to be true of our y. Okay. So first of all, in order for a class to be unstable, that roughly means that I don't have any points that are sitting still out at infinity. And what this theorem says is that there's from range R of I where I have at most R of I points that are moving around the manifold, and all of the remaining points are in these orbiting pairs out in this copy of Euclidean space. So
There are no fixed points out there.
I beg your pardon, there are no fixed
They're
points.
trying to retire, it's like semi-retire.
Yeah, that's right. These are the
They're out there, but
unstable.
they're still moving a little bit, and then they're going to retire later.
Take that personally.
Okay, so let me draw a second picture to help us visualize what's going on here. So this is a picture of all my homology. So here's the k-axis and here's the I-axis. So along each of these rows, I have homology in a given degree. And so let's say I'm looking at a surface for this. So first of all, the homology is going to be 0 outside some range just for dimension reasons. Okay, this is probably like k equals I or something like that. And up here everything is 0 just because that's above the homological dimension of the configuration spaces. And then the first,
Well, 2 are,
so the Church-Ellenberg-Farb results says that if I look along these rows of my homology, then they stabilize past this line. So past this line, I have no more unstable groups, and everything is sort of induced up in some deterministic way from the stuff in this range. And so what our theorem says is that in this quadrant where we have unstable homology, it's not a quadrant, in this triangle where we have unstable homology, then you can look along these lines like this that have, they should have slope 1/2, I've drawn this in a skewy way, but along these lines, you also get stability with respect to this operation.
oh, this goes this way.
Yeah, that's right. So our theorem is looking specifically at the unstable groups that all exist in here. And now we're moving diagonally along these lines, and we get stabilization along there with respect to this operation.
You're moving parallel to the k equals 2I line?
Yes, that's right. These are all parallel to the k equals 2I line, which should be less steep than I want it. I have poor drawing specs, apparently. Okay, so let me, oh my gosh, I'm out of time. Let me quickly make a final comment. I said this is most interesting in the case when M is a surface, and that's because when M is a higher dimensional manifold, this class here is actually 0 in homology. So this class, I can just cap this off by letting the point labeled k plus 1 run everywhere in a disk above the other point. And so this is 0 in homology in a higher dimensional manifold. So in higher dimensional manifolds, the theorem just says that a whole lot of unstable homology vanishes, and in fact you get a better representation stability range for these groups. But for surfaces, these classes can be non-zero, and in that case, this is a real phenomenon. Okay, that's everything I wanted to say. Thank you.
Any questions?
So what is the final theorem now, higher than
What is the theorem for higher dimensions?
No,
Well,
what is the finer theorem? I'm using this last fact to get a better stability result.
oh, that's right. So this last fact you can use to say something like actually things stabilize when k is I instead of when k is 2I. I think that's right.
Okay, that's what you indicated. Okay.
That's right.
So 3 manifolds and higher stabilizes with I, maybe.
That's right, that's right. And I should also say this improved stability range is something Churchill and Berg and Farb knew for orientable manifolds.
Right.
And this gives
General, new proof, and
a new proof, and it works for a larger class of manifolds.
it's only for rational coefficients.
That's right. This is only for rational coefficients. Oh, and I did write that here. I'm sorry. I should have done so. So the main theorem is for rational coefficients. The reason it's for rational coefficients, again, is in the background, we're understanding this is the module, the sequence of the module over some category that's encoding both the stabilization maps and the symmetric group actions. And our proof critically uses the fact that this category is Noetherian. This was a proof result due to Nagg, Powell-Sand, and Snowden. But right now, this Noetherian property is only known for rational representations of this category. And if we knew it integrally, then we could, the rest of the machinery works integrally. But these results are quite hard, so right now we only know it rationally.
So, at the beginning, you started with unordered configurations, and then you switched to ordered.
That's right.
And in the case of unordered configurations, everything was much simpler because these actions of group.
That's right. There's no symmetric. I mean,
So
you know.
my question
I won't
is
say it's
about
simple, but-
relations of your results to that unordered situations. Do they disappear there and follow from what was known, or there is something here about unordered configuration?
Something new. Oh yeah. So right. So I think I mentioned before that rationally you can recover classical stability, homological stability down below from the representation stability of the covering spaces. So we can representation stability rationally for the ordered configuration spaces implies homological stability rationally for the unordered spaces. Not so
What about ability to deduce results about ordered configuration from unordered?
To go, the unordered, that's right. So somehow the unordered sort of sees the trivial component of the SN representations up
So
above.
representation theory is in between.
So right, that's right. So there's sort of more going on upstairs. It's also interesting. So I think Melanie Wood has a student, Megan, who's been working on understanding relations between unstable homology for the unordered configuration spaces. And interestingly, so this result does not say very much about the unordered spaces for the reason that if you introduce if I stabilize twice, if I introduce an orbiting pair and then I introduce a second orbiting pair, then those homology classes are anti-symmetric with respect to the action of the symmetric group. And so they vanish. When you take coinvariance, it's all 0. They don't show up down below. And so that's right. So somehow our theorem does not say very much about the unordered configuration spaces, although there are things going on down there between the unstable homology groups. So it would be interesting to understand better how that's reflected by the ordered spaces. But I don't know that right now. Yeah?
I just realized when I walk out of here and I think about this, I'll be able to remember some of the statements, but I won't know anything about how they're proved. Is there anything you'd like to say about some of the proofs?
Oh.
I mean, just an idea or two of proofs.
Yeah, so the idea, what we did was we looked at some, we studied certain semi-simplicial spaces called the arc resolutions that you can build up from these configuration spaces. And associated to these semi-simplicial spaces, we get these geometric realization spectral sequences.
picture of that, though?
Spectral
Arc
sequences. So the picture of the arc resolution is a p+1 simplex is built as follows. So I start by taking my manifold and I choose a interval in the boundary. Regardless of the dimension of my manifold, I always choose a one-dimensional interval in the boundary. And then a p-simplex is given by a point in my ordered configuration space plus a choice of p+1 embedded arcs. Embedded arcs from that interval in the boundary out to the point. They do not cross. They cannot cross. They can only intersect one point in the configuration. They have to avoid the other ones. And so this is I can define face maps by just forgetting the ith arc. There's an order induced on the arcs by the order on the boundary. And then, right, so this is a semi-simplicial space, and I get an associated spectral sequence. And so what we did was we studied the differentials in this spectral sequence. We did some computations. It turns out you can understand these combinatorially, both in terms of the homology of the configuration space and also this combinatorial object called the complex of injective words, which is a classical object from algebraic topology. So we did some computations with that.
I didn't hear the word. What was the word?
The complex of injective words.
Oh, objective words. Okay.
That's right. It's something you can use it, for example, to prove homological stability for the symmetric groups, for example. And so we studied the spectral sequence by doing some combinatorics and by computing the D2 differentials in the spectral sequence and showing that somehow those D2 differentials, in a sense, at least in one column, are actually the stabilization map here. And so from that point, we could run some sort of Quillen-style inductive argument
What style?
on
Quillen. Quillen.
Oh, Quillen style.
yeah, Quillen style, and the way Quillen introduced this argument for proving homological stability for things like linear groups. This method of running induction on a family of spectral sequences. And so we sort of adapted that method to this equivariant setting and used that to prove the main results.
Let's thank the speaker.